Hello, good day, viewers. I'm Emmanuel. Sorry, and today we'll be talking about cache memory. Talking about the cache memories, yes. Talking about the cache memory. But our main topic is about the cache mapping techniques. Yeah, we're talking about the three types of the mapping techniques, which is the direct, the fully associative, and the stepping associative. So we'll be diving in deep today, but I want us to first brief on the cache memory itself, the definition, the operations, the levels, the locality of references before we move to the mapping aspect. So let's define cache memory. What's a cache memory if you ask? It's a cache memory. Well, my definition to cache memory can be cache memory is a very small, fast memory located close to the CPU. Yes, as you all know, the CPU. CPU is in the system unit. Yes, CPU is the motherboard. CPU is on the motherboard in the system unit, as you all know. It is used temporarily to store data that the CPU is likely to use again. That is the cache. So the cache function, this function is used to temporarily store data that the CPU is likely to use again soon. The reason cache exists is because there is a big speed difference. Yeah, there's a big speed difference between how fast the CPU can operate and how fast the CPU can operate and how fast the main memory, which is the RAM, the main memory, which is the RAM, can provide data. Yeah. So cache helps bridge this speed gap. When the CPU needs data, it first checks if it's in the cache. And if it's in the cache, you call that process the cache hit. The cache hit. Talk about the cache hit. It accesses it quickly. If the data is not in the CPU, then we call it a cache miss. Cache miss. For the cache miss, it fetches it from the slower main memory. Well, the cache improves system performance by reducing waiting times and increasing processing speed. Yes, that is the cache. So now let's here from our slides we say cache is a small fast memory. This is a summary slice. Small fast memory located very close to the CPU. It stores frequent data, holds the information the CPU needs often to boost performance. Yes, reduces CPU waiting time for data. Yes. So now let's move to the cache operations, which are the read, write, hit, and miss. Which are the read, write, hit, and miss. For the read, understanding how the cache works involves knowing these four key operations: the read, write, hit, and miss. Now let's start with it. The read. For the read, we say the CPU wants to get data from the memory. That is the CPU requests data, wants to get data from the memory. And the write, when the CPU wants to store data into the memory, we call it write. For the hit, as I recently explained what is a cache hit, that's when data is found in the cache. The hit is the requested data. It's already in the cache. Yes, that's the hit, and the CPU can access it quickly. So the hit is the data found in the cache. And the next one is miss. Miss is the data not found in the cache, which is fetched from the RAM. So if the data isn't in the cache, it's a miss. It's a cache miss. And the CPU must fetch it from the main memory, which is slower, and that's the RAM. Well, take note of this. We say more hit mean faster performance. Why do we say this? This is because less time is spent waiting for data. Now, let's take a break and move to the cache levels. Let's move to the cache levels here. Cache levels, we have level 1, level 2, and level 3, which we will write it as L1, L2, and L3. L1, L2, and L3. L1 cache is the smallest, fastest, integrated with the CPU core. The L2 is larger, slightly slower, often shared per core, as is on the slides. The L3 is also the largest, slowest, shared across all the CPU cores. Now let me break it down for you. The L1 cache. So you all know is the fastest and smallest. It's built into the CPU core. Someone also say it is integrated. Yeah, as it's on the slides, we use integrated on the slides. And I've used another word called the built. Yeah, so it's built into the CPU core. The L2 is slower and larger than the L1. It's either shared or assigned per CPU core. The L3, the largest and slowest among all. Now, take note, data moves from L1 to the L2 and to the L3 depending on how frequently it is accessed. L1 is checked first for data, then it moves to the L2 and then it moves to the L3 as well. As we proceed, we're talking about the locality of reference, which is why cache works. Why the cache works. Cache memory is effective because of something called locality of reference. Locality of reference. We have two types of locality of reference. Today we're talking about it, but we are not moving deep into it. Now we have the temporal locality and we have the spatial locality. For the temporal locality, if the CPU accesses a piece of data now, it will probably need it again soon. And that's the temporal locality. If an item is referenced, it will be referenced again soon. And we call it a temporal locality. For the spatial locality, if a piece of data is accessed, nearby data will likely be accessed next. If an item is referenced, nearby items will be referenced soon. And that's the spatial locality. This prediction allows cache to load data intelligently, increasing hit rates and improving performance as well. Let's continue on to the main topic, which is the cache mapping techniques. So this is the main topic that we'll be diving deep, the main cache mapping. That's how data is placed, the time why mapping matters as well. Introduction to it. When storing data into cache, we need to decide where, the word is where to put it. This decision process is called cache mapping. How data is placed. It determines where main memory blocks go in cache, ensures rapid data lookup. Why mapping matters? Let's move. Cache mapping is important because it helps the CPU quickly find where the data is stored in cache. Cache mapping helps the CPU quickly find where the data is stored in cache. The method used affects how fast and efficiently the cache works. Now, why mapping technique matters? Have you thought of it? Why mapping techniques matters? Here we have avoid data conflict. Yes, it avoids data conflict. It makes sure memory blocks don't overwrite each other unnecessarily. Yes, second point, we will say it maximizes cache hit performance, which means better performance. It reduces cache misses. And reducing cache misses means the CPU can work faster and more smoothly, which boosts the performance as well. And some will say we have the third point, can also say increases hit. Smart placement increases the chance that needed data is already in cache. Yeah. Now let's move to the first type of the cache memory mapping. I already told you we have three types of the cache memory mapping, and that was the direct mapping, fully associative mapping, and the set-associative mapping. Now we are moving to the direct mapping. The direct mapping is simple but limited. Each main memory block maps to one specific cache line as it is on the slides. This modulo operation blocks addresses modulo number of cache lines. Direct calculations, no complex search. High conflict here. Different main memory blocks can map to the same cache line. So let's dive deep. Direct mapping is the simplest method here. Each memory block goes to only one specific cache line using a modulo operation. It is fast and easy to implement using the hardware. However, it has a big problem. And the problem is if two commonly used blocks map to the same line, they overwrite each other. This causes a lot of messes known as conflict messes, and that's the problem that the direct mapping has. Let's move to the next type of mapping, which is a fully associative mapping. Fully associative mapping. Sorry, my PC is on a low power. Fully associative mapping, and that is flexible but slow. This method is flexible. I don't even do more. This method is flexible but slow. Yeah, a memory block can go to any, the word is any available cache line. Any available cache line. This reduces the conflict messes because there's no fixed location. Yes, but it requires complex hardware like CAM. The CAM is the CAM, which is the content addressable memory. Content addressable memory to search all lines at once is slower and more expensive, but very efficient in handling data placement. That's the fully associative mapping. It's flexible but slow, requires searching every cache line to find data. Now let's continue on to the last one and we will end our session, which is the set-associative mapping. The set-associative mapping. This method combines features of both previous techniques, a hybrid approach combining the best of both direct and fully associative mapping. So the cache is divided into sets. Each memory block maps to a specific set, like direct mapping, as a direct mapping. Inside the set, the block can be placed in any line, like the associative mapping that we just talked about, the first one, the fully associative, that's it. This makes it a balanced, choiceless conflict, that direct mapping and simpler than fully associative. Any line in set within that set block can go into any line, like the associative mapping. Let's move to the last slide. Just wanted to add this thing, which is the comparison. For the comparison, let's compare the three. The direct mapping is fast and simple, but high conflict messes. For the fully associative, it is most flexible, lowest conflict, but expensive and slower. And for the last one, which is set associative, we have a balance between both, good performance with moderate complexity. Choosing the right techniques depends on your goal, speed, cost, or reduce messes. Thank you. We end our session here and we'll continue another time. Goodbye.